I want to start by reminding what we learned about the sum of internal angles of a triangle. So given a triangle whose angles are like A, B, and C, we physically check that when you have angle A, B, and C, that you can glue them in this order and check that the sum of internal angles is 180 degrees. It naturally begs the question of whether this is true for a quadrilateral, a pentagon, or a hexagon. Now, unlike for a triangle, the catch here is that the sum of internal angles for other polygons can be deduced from triangles. Before we jump into how we figure out the sum of angles, I want to set up some terminology here. The reason is because we have more than 4 sides and 4 vertices, the position of sides and vertices will matter. And when we're describing things, we need to prescribe how they're positioned relative to the other. So given a polygon like this, when you have 2 edges sharing a vertex, we call them adjacent sides. Adjacent here means they're neighboring or they're touching. Obviously, when you have 2 sides sharing a vertex, they form an angle. If 2 sides don't share a vertex, on the other hand, then they are non-adjacent. Now we can do the same principle with vertices too. When you have 2 vertices not sharing a side, then they're non-adjacent. If they do share a side, we call them adjacent. Now any line segment connecting 2 non-adjacent vertices is called a diagonal line. Now, if the angle formed by 2 adjacent sides is facing toward the interior of the polygon, then it is called interior or internal angle. Now you may wonder what exterior angle is. So the exterior angle is defined by extending one of the sides. So you can see this blue ray right here, and measuring the angle between this extension to the other side. And simply you can think of that as the supplementary angle to the internal angle. Now how do we figure out the sum of internal angles for quadrilaterals? We can start with a quadrilateral, and of course we can measure all the angles and try to glue them together and figure out that they form a 360 degree, a full rotation. Now you can try this for other shapes like these, but at some point, for example, if you look at this kind of L-shaped quadrilateral, you'll figure out that it's perhaps easier to cut the quadrilateral into half and try to measure angles and then add them up. This is called the subdivision, and this is the strategy that we're going to take. Now, as simple as it sounds, we have multiple ways of cutting the quadrilateral and cutting the polygons. So here's the first method. So this is motivated by making a hexagon. So if you have an equilateral triangle like this, I can form a regular hexagon by 6 triangles. And knowing that each triangle is equilateral, I know that this angle here is 60 degrees. I have another 60 degrees, so I know that each internal angle of a regular hexagon is 120 degrees. So this gives me the sum of internal angle for a hexagon is 720 degrees. So you can see that I'm drawing 3 diagonal lines going through this center point. So if I have any kind of polygon, for example, here's a hexagon, I can just pick a point in the center and try to connect the line to every vertex and divide that into 6 triangles. So I know angle inside each triangle adds up to 180 degrees. This is what we figured out. Since we have 6 triangles, all the angles add up to 1080 degrees. But angle inside the hexagon at the center, that's 360 degrees. So by observing that, the sum of internal angle is 1080 minus the angles at the center, that's 360 degree, which is 720 degree. You notice that these two angles are consistent. So let's try this strategy for other polygons too. I can start with a pentagon, a hexagon, and this is a heptagon. So the strategy is you pick a center and you connect to every vertex. You pick a center, you connect to every vertex. You pick a center and you connect to every vertex. You notice that I didn't make any assumption about polygon being convex. This strategy also works for concave polygons, by the way. So, how many triangles do I get? Well, I get 5 triangles for the pentagon. I get 6 triangles for a hexagon. I get 7 triangles for a heptagon. So the angles, the sum of the angles will be 180 times 5 for a pentagon, 180 times 6, which is 1080 degrees for a hexagon, 180 times 7, which is 1260 for a heptagon. Now, just like last time, I had this extra 360 degree angle at the center. So all I have to do is subtract that off. So 900 minus 360 degree, that gives me 540 degree. And for a hexagon, that's 1080 minus 360 degrees. So the sum of internal angles for a hexagon is 720 degree, which is what we just checked. For a heptagon, that's 1260 degree minus 360. That gives me 900 degree for the sum of internal angles inside the heptagon. So let's look at another strategy. So we go back to this quadrilateral, which looks like an L shape or an arrowhead. And we were talking about cutting that or slicing that into 2 pieces. So motivated by that, if I have a hexagon like that, I can try to split this off into 4 different triangle pieces. So this is the second subdivision method that we're going to look at. So if we have a pentagon, a hexagon, and a heptagon. Okay, so one way of cutting them into triangles is that I could introduce 2 lines, 2 diagonal lines in fact, and split them into 3 pieces of triangles. So I have 3 triangles. For a hexagon, for example, I can try to split that into 4 triangles. And same strategy for heptagon. I can pick a vertex and then try to connect to other vertex by introducing diagonal lines that does not cross other diagonal line. And that gives me 5 triangles to think about. So the sum of angles will be 180 times 3, that's 540. 180 times 4, that's 720 degrees for a hexagon. 180 degrees times 5, which is 900 degrees for a heptagon. You'll probably notice that having 3 triangles, so that's 3, instead of 5. So it is always 2 less than the number of sides you get for the number of triangles. So for a hexagon, this is 6-sided. But you get 2 less, so that's 4 triangles instead. Same thing with a heptagon. You have 7 sides, and you get 5 triangles. So if you have, say, a pentagon or a decagon, well, how many triangles should you get? Well, I don't know how to draw triangles, but I can easily guess that there should be 8 triangles using this kind of strategy. And the sum of angles must be 180 times 8, which is 1440 degrees. Now try to come up with 8 triangles on your own for this star shape. It'll be an interesting exercise. So in this part, I want to talk about some physical intuition behind the sum of internal angles. So this is one moment where we get to see the application of external angles. And we don't really talk about this in the packet. So I thought it was some cool introduction to how we view things geometrically using physics. So let's go back to defining a polygon. So I mentioned that a polygon, to form a polygon, is like you go straight and then make a turn, then make another turn and try to come back to the point where you started, right? So imagine yourself driving through a road like this. So you try to go to this red direction, and then you're making a turn to go to point 2, and then at point 2, well, you try to go to the red direction, but then you'd make a turn, and then at point 3, because we're making a loop, you have to make another turn. So in effect, that you're making it, so if you're only focusing on the direction, you make this amount of angle turn, and then here's another amount of angle turn, and then you make amount of another angle turn at point 3. Since we're forming a complete loop, you can deduce that the sum of external angles must be 360 degrees because we're making a complete loop. Now, the reason we don't talk about this is we have to keep the track of in which direction that we're making a turn. So here we're making a clockwise turn, and so you have to make a clockwise turn, a full rotation to come back to where you started. So how does that actually work in other polygons? So I can take a hexagon. So let's start a trip on this top. So I'm trying to go to this red direction and need to make a turn. I try to go to the red direction and make a right turn. Try to go to this red direction and then make a left turn. Try to go to the red direction and now I'm making a right turn again, making a right turn and making a left turn. But in effect, the sum of all the external angles, because I'm making a loop, must be 360 degrees. So since internal angles are just supplementary to the external angle that I can figure out for a triangle, the sum of internal angle must be 130 times 3 minus 360, which gives me 180 degrees that I wanted. Same thing with a hexagon, that I can do, I have 6 angles, or I'm making 6 turns, so that's 180 times 6 minus 360, that gives me 720. So you can actually interpret this physically as well, just knowing that to make a full trip, you're making a 360 degree turn in the change of the direction, and from that you can deduce that the sum of internal angle must be following this kind of formula pattern. So let's do a quick summary. So by subdividing into triangles, we can figure out the sum of internal angles for any polygons. And we had 2 methods. One was to pick a point in the center and then draw the same number of triangles as the number of sides. Whereas the second method, you would draw 2 less number of triangles compared to the number of sides. So for a hexagon, if you're using the first method, you would have 6 triangles. Whereas if you're using the second method, you would have 4 triangles. But the result you get will be consistent because you're subtracting by 360 degrees for the first method, but not for the second method. We also talked about some physical intuition and some applications of external angles, that using the fact that to make a complete loop, you have to make a turn and then change the direction in 360 degrees. And using that, you can figure out the sum of internal angle must be following the same formula as the method that we discussed previously. So thank you for watching, and I'll see you next time.